Yamadaka.
Thì nó chỉ là guarda che fanno la No problem.
I want to take your original.
Thank you.
Right for me, okay. Like play game.
Give. I attend class.
Okay. Okay. Now your alpha where you last stop.
Na Zoom we do. Don't say the matric number.
Okay, you don't enter. Now online this thing they do. Jerry the same thing.
Say?
Jerry. Hey, like I go meet people there next. They play. Please that for you. I feel like those things that.
Right, Jamie.
We fight yesterday. For you. Hey.
Angeloki, you mute yourself now.
I don't think I'm out my place. So good. You want to go? More. What you want me to do? You need that. You need that. That's good. You know the location. Mine.
Please, if you know that you are not muted, everybody mutes. I'm starting the lecture. If there's unruliness, I will assume I've finished. I will assume that I've finished teaching. Please, let's go that route. So good morning, everybody. Our last class.
Good morning, ma.
In our last class, we talked about. I told you the course outline for today's lecture. For this course, introduce myself. Told you that we are talking about acid-base, salt, and redox titration, and a little introduction to electrochemistry. So these are the learning outcomes. To identify this, and identify balance of redox equation, and solve problems related to that. And I started with telling you that in nature there are different types of food. We have sour, sweet, bitter. Just like that, in chemistry, we have different types of substances that can be classified as acids, bases, or salts. I told you there are three major classifications for three major definitions of acid bases and acid bases. We have the Arrhenius definition, Brønsted-Lowry's definition, and the Lewis definition. Arrhenius definition is based on H plus addition of H plus. That is, a proton must donate H plus, while a base produces OH minus in aqueous solution. And we went into details as to why there were limitations with this theory. We went into limitations of this theory. And I better captured it today in 6 points. The limitation of the theory is that, of the Arrhenius theory, is that the hydronium ion must be produced, as the H2O plus must be produced, or OH must be released by acid and base. And this condition does not account for weak bases. Does not account for weak bases. Another thing says that for a substance to be an acid or a base, there must be presence of water. Water is necessary for it to act as acid and base. But that is not true, because gaseous HCl, gaseous ammonia still acts as acid or base. It does not explain the acidity and basicity of substances in non-aqueous solvents. There are non-aqueous solvents where substances do behave as acids and base, but it doesn't account for it since everything must be in water. And neutralization reactions involves this formation of salts in the absence of a solvent. So no, it's saying that salt only occurs in aqueous solution, but that's not true. You can produce salt even in dry solution if the right condition is there. It doesn't account for the acidity of substances like aluminum chloride. It doesn't account for it. And to explain the basicity of ammonia, we need to make some assumptions. It doesn't readily explain the basicity of ammonia. So I was able to capture my thoughts in points. These are the summary of the limitation of the Arrhenius theory. I explained it in the last class using these equations, but now I've captured my thoughts and written it out. Then I went ahead to talk about, further explain, which I've said that I've talked about. This is another example of how Arrhenius theory does not support gaseous substances, which I've itemized in this summary. Like this one now, this is not a acid, and this is not ammonia is not an acid, and it's not a base, and HCl is not an acid because it didn't occur in a gaseous scenario. I mean, it didn't occur in a aqueous solution. Whereas in gaseous scenario too, we can still have substances behaving as acid and base. Arrhenius equation would not explain this situation. I went on to the Brønsted-Lowry's definition of acid and base, where I told you that Brønsted-Lowry's acid is anything that increases a proton, and Brønsted-Lowry's base is anything that decreases the concentration of proton or accepts a proton or donates OH. And Brønsted-Lowry's definition is very vast, is wider than the Arrhenius theory. With the Brønsted-Lowry's equation, definition of acid and base, we can account for the for weak ionization of water. That is the auto-ionization of water. I mentioned it in that class. We can account for acidity and basicity of substance. We can account for the ionization constant, or dissociation constant of acids and bases, even weak salt. We can do a lot. We can calculate the concentration of hydrogen ion in solutions. We can calculate the concentration of OH ions in solutions. We can account for conjugate acid and conjugate bases of acids and base, and lots more. So it's broader. There's some, and I delved into some of these things that we can account from the Brønsted-Lowry's equation. Yes. So another thing I want to tell you is, okay, when we get there, So these are some of the things we did. We talked about acid. I did this quiz, and I was trying to explain conjugate acid and conjugate base pair, conjugate acid and base pair. So I gave you some example, and some people didn't get it. So I went to search out and bring this for you to understand. Looking at this now, you see that H2O is the acid in this case, and its conjugate base is the OH minus. This happens in auto-ionization of water. You see that HCO3 is the acid, and the conjugate base is the CO3 2 minus. So you see that the conjugate base has one hydrogen less than its source, its acid. That's what thing you need to look out for. I gave you a quiz and many people didn't understand. So I said, probably I didn't teach you. Let me go and get more samples to explain it. The conjugate base always have one hydrogen less than its originating acid. Look at the SO4. SO4 2 minus is conjugate acid. The base is the conjugate base, and look at its acid, HSO4 minus. And so on. You can see that trend in ammonium ion and ammonia. So here, ammonium ion is the acid, is the conjugate acid, while ammonia is the base. Ammonium ion is the conjugate acid, while ammonia, sorry, I've mixed that line up. Ammonium ion is the acid, while ammonia is the base, because it's less than the other entity by one hydrogen. Again here, this CH3 NH3 plus is the acid, and this is its conjugate base, because it's less than by one hydrogen. So that's how you always know which ones are acid, conjugate acid, or base pair. So they can either be conjugate acid and a base, or a acid and a conjugate base. So that's what's happening here. So that's the relationship. So I got some more examples to buttress the point I was trying to explain last class. And in my last class, one of the fallout of Brønsted-Lowry's theory is that we can say we have monoprotic acid, polyprotic acid, and we can write the ionization constant for different ones based on how they dissociate when in solution. So we can write the dissociation constant for them, or also called the ionization constant for them. So we have, if it donates only one proton, we have monoprotic acid. If it donates more than one, we say it's polyprotic acid. And under polyprotic acid, we have diprotic, we have triprotic, and many more. I talked about the auto-ionization of water and the fallout. So because water can undergo auto-ionization, it can act as an acid and it can act as a base. So that's what I'm trying to show you. It acted as an acid in this conjugate pair. It acted as an acid. In the other conjugate pair, it acted as a base. Hope I'm recording. So, and then, so because it can do that, when we write the dissociation constant, we have this equation. It's always product over reactant. When we are writing the dissociation constant, we never write water in the liquid state in any equation we write. So because water is the solvent, so we can't estimate the concentration in relation to the products that are in little concentration. So we usually do not write water if water features in the equation. Water as a liquid, you don't write it. And so that's why over nothing, let's say one. So the concentration of water will be given 1. So it won't show. So anything over 1 is the thing. That's why water is not there. So it's product over reactant. And so that's why we got this. And we are saying that by the time you prove this equation is also equal to Ka times Kb. That is the Ka, where A is the acid, and B, where Kb is the base. So the concentration of base is equal to the dissociation constant, the acidic dissociation constant. The concentration of the OH minus is equal to the dissociation constant of the base that was involved in whatever reaction. And so that's how we got all these equations. And in pure water, this is always what happens. You have the concentration always 1 times 10 raised to the power minus 7. In pure water at equilibrium, this is what will happen. And this dissociation is this auto dissociation is very small. And that's why water is a weak electrolyte. Very small. The concentration is very small. And I explained that's why water is a weak electrolyte and a poor conductor of electricity. But it's a unique solvent because on its own, it can act as a base, it can act as an acid, and can undergo auto-ionization. You need to know this. I'm sort of going over the last class again, just to emphasize many things because you are year 1 student and this is my first interaction with you. I want to get another source of internet. Hello, is anybody there with me?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So I'm just going through what we've done. And so I said that if you have the hydrogen ion equal to OH, if you have a neutral solution. If you have this greater, you have an acidic solution. And if you have the hydronium ion greater than the hydroxide ion, you have you have a basic solution. And once the concentration of the hydronium ion increases, the hydroxide ion would always decrease, and vice versa. So, and then one equation you must note is this relationship that Kw is equal to the concentration of OH minus times the concentration of H3O plus. H3O plus. You must always note that that equation is key in solving many problems. And Kw is always equal to 1.10 times 10 raised to power minus 14. Kw is always equal to that. So the OH concentration or H3O plus concentration may vary. And so if you know that, you can calculate the concentration of hydrogen ion or hydroxide ion in any solution. And I gave you some things to calculate. And if you know that, if you know this, you can also calculate pH of solutions, pH of various solutions, because you know that pH is equal to minus log H, minus log H concentration, H plus concentration. pH is also that. pOH is also equal to minus log OH minus concentration. We'll be looking at that shortly. And so we wanted to start talking about strong acid, weak bases when you said my time was up. Now, strong acids are molecular compounds that ionize to completion in aqueous solution. They would dissociate into and give you the H plus. You know that H plus can be written as H3O plus plus. H3O plus. That is in water, it will give you the H3O plus. But if it's not in aqueous solution, then strong acid, that's why it's better to say a strong acid is any substance that is going to give you H plus. H plus can occur in non-aqueous solutions too. Now, there are few strong acids, then all others are weak acids. I know many of you know some strong acids, HCl, H2SO4, HNO3. These are some of the few strong acids we have. Most of the other acids are weak. Weak acids will not dissociate completely to give you the H plus ion. Will not dissociate completely. It will dissociate weakly. So if you had 100 molecules of weak acid, probably let's say 1% or 2% of it is what will actually dissociate to give you the H plus ion and an additional ion. So the same thing goes for weak bases and strong base. A strong base is a molecular compound that ionizes completely to give you OH minus ion and a cation. While a weak base would ionize in solutions but weakly to give you OH minus. So not all of it will go. Unlike strong bases, 100% of it. If you had 100 molecules, you can say you have 100 molecules of OH minus. But in weak bases, if you had 100 molecules, you can't beat your chest and say you have 100 molecules of OH minus in solution. No. Maybe you have 10 or 20 you have tried if you have that. So that's what we're trying to say. And so for strong acids, when you're writing it, and strong base, when you're writing the dissociation, you use this type of arrow. But when you're writing this type of equation for weak acids and weak base, you use the equilibrium sign. There's a forward-facing arrow and a backward-facing arrow when you're writing its own dissociation constant, because it's not absolute. Yes. Now there's a question for you to solve. A 1 molar solution of this acid in water contains this concentration of hydrogen ion and this concentration of ClO. This concentration of this is conjugate base. Yes, it's conjugate base.
What is C of?
But so we are looking at the example now. A substance, this particular acid. So because it's an acid, its other part is the conjugate base. So this conjugate base has, so when it dissociates in water, you got this concentration of, if you got this concentration of acid and this concentration of base, conjugate base, we can't say this is a weak acid because it has equal amount of H plus and equal amount of conjugate base. Look at the concentration, 1, 1. It started with 1 mole. It means everything dissociated to give us 1 mole of its conjugate base and 1 mole of its hydrogen ion. So that's a strong acid. That means it's a strong acid. So weak acid, example will include this: acetic acid, ammonia. They would only dissociate with full percent, maybe like 1%, like you would wait, because there's something, there's a point I must get to. If not, your exams are coming, and then please wait. There's going to be a time for question and answer. Kindly bear with me. I need to move. Thank you. So that my thoughts too will flow. So that my thoughts will flow and you don't cut me along my thoughts. So these are some examples of strong acids. These are some examples of weak acids. And so weak acids produce good quantity of weak acid will produce weak conjugate bases that can be measured. For strong acids, we can't really measure the conjugate base. So most times when we have weak acids, we can measure the concentration with conjugate base. But for strong acids, if you know the concentration of the hydrogen ion, you can already automatically know the concentration of the conjugate ion. So we really do not measure the concentration of the conjugate ion. Acetic acid is a weak acid. So its conjugate base will be this. That's the acetate ion. Acetic acid is a weak acid. How do you know weak acid? By the Ka. Because this Ka, you remember Ka is equal to H plus from that auto-ionization equation and dissociation constant of our water. You know Ka is equal to H plus. in a substance. So this is the Ka of the acid, and this is the K of the acid. So since acetate, we can calculate the Kb, the concentration or the Kb of the base, because we know that Kw, who can tell me what Kw is? The value of Kw is fixed. Who can tell me what the value of Kw is? If you know.
1.0 times 10 raised to power minus 14.
So if you have that, and we have been given Ka, sorted. Remember that Ka is equal to H plus, concentration of H plus. So if you have Ka or H plus, it means you can find Kb. So that is how we found this. And so for weak acid, Kb, for weak acids and bases, Kb will be low. Kb will be low. Kb will be low. Kb will be low. But for large, for strong acids and strong base, you know, Kb is equal to the concentration of hydrogen ion or OH. Kb is equal to the concentration of OH minus. Ka is equal to the concentration of H plus. H plus. So when you have plenty H plus, it means we have plenty big Ka. When we have plenty OH minus, it means we have big Kb. But we have few as in weak acids, then we'll have small amounts of
H plus.
if we have small low Ka, we have small amount of H plus. If we have small Kb, we have small amount of OH minus. Strong bases, most group 1 and group 2 metals give us strong bases. And every other base that is not from group 1 or group 2 on the periodic table are weak bases. So I can bring up different things and tell you which one is a weak base, which one is a strong base. Once you know your group 1 metal elements, once you see it attached to OA, just know it's a strong base. Once you don't see it, any other thing, a weak base. And so any acid or base is technically a conjugate acid or conjugate base also. That is, any acid you know can be a conjugate acid to a base. Any base you know can be a conjugate base for another acid, vice versa. So just by looking at how that particular stuff dissociates, that you know which is which. Now, weak acid, these are some examples of some weak acid. These are some examples of some.
We shop clothes. We shop.
These are some examples of some weak bases.
This red.
If an acid is strong, you cannot measure the conjugate base, the strength of the conjugate base, but you can estimate it because you know that 1 mole of a strong acid will dissociate to give you 1 mole of H plus 1 mole of the conjugate base. But you can't measure it really experimentally, but you can estimate it. But if you have a weak acid, weak base, we can make some measurements with conjugate base or conjugate acids. The strongest acid you can ever have is the H3 in solution. Is the H, sorry, this equation is wrong. Is the H3 the hydronium ion. That's the strongest acid you can ever have. While the strongest base you can ever have is the OH minus ion. Acid stronger than H3. I want to be sure this is recording. Acid stronger than the acid stronger than H3O plus reacts with water to produce the hydronium ion. They are conjugate bases. So in essence, in water, in aqueous solution, the strongest acid you can have is H3O plus. In other phases, maybe in non-aqueous solution, in gas, You might have other stronger acids, but in aqueous solution, the strongest acid you can have is this NCT. So I don't want to go into all that. So, okay, so let's look at this. Let's do some calculations. Calculate the pH of this HCl in solution. So how are we going to do it? We know that pH is equal to minus log hydrogen ion or minus log H3O plus ion. And here you've been told that the concentration of HCl is this. This is a strong acid. This is a strong acid, so we dissociate to give you what? The same mole. If you dissociate, 1 mole of HCl will give you 1 mole of H plus and 1 mole of Cl minus. So all you just say, you just use this concentration right away. pH is equal to minus log 1 times 10 raised to the power minus 3. What's the answer? What's the answer?
3.
3.
I've done it, but I didn't write it out. Okay, I'll show you the answer soon. The same way you calculate all this. Let me show you the answer. So HCl will dissociate to give you this. So the question said 1 times 10, yes. So this is how to work it. The beginning, no. But you know that when it dissociates, it will give you exactly the same amount. Why is it giving you the same amount? Because it's a strong acid. If it's a weak acid, you can't say it dissociates to give you the same. If it's a weak acid, they'll tell you the percentage dissociation. You calculate the quantity that it will give. But strong acid will give you this same thing. So you can say minus log that and you get 3. So those who got 3 had it. The same way we can go on to calculate for this, for barium hydroxide. Barium hydroxide is a strong base because it's a group 1 or group 2, is a group 2 element. So it's a strong base. So the same thing, but here 1 mole will give you 2 mole of OH. So you multiply what you are given by 2. Yes, 1 mole will give you 2 moles. So you multiply by 2, and that gives you that. But you know that you can either do it this way, minus log H, but we don't know the concentration of H. We don't know. They told us calculate the pH of this. Okay, now, so with this, they were not told the concentration of H. What we can find out from this statement is the concentration of OH minus. So since it's concentration of OH, we would find the POH, which is minus log this. And then we'll subtract it from the scale. Because pH is actually, pH quantifies the hydrogen ion. I remember from that KW that I told you that that KW found out that in every solution, you always have H plus and OH minus, and OH minus. And so if you know the concentration of OH, you can always find the concentration of H plus. And we know that the scale is 14. So we do this, the scale, the pH scale is 14. So 14 minus this will give us the pH of the base. Brought this example so that you would see how it works. Look at number 3. So the same way we calculated for B is the same way we are going to calculate for C. So here we'll multiply again by 2 because 1 mole of this gives you 2 mole of OH. So multiply this by 2 and we'll calculate the POH. But pH is actually for hydrogen. So remember, I think I showed you something. See here, have I got where I showed you? Showed you something. Okay, not here. I'll show you. Okay, I didn't put it here. So this is the hydrogen, the pH scale. So when you get your OH, OH takes up So when you get your OH, you know in a solution, you always have OH ion and hydrogen ion. When you calculate the OH ion, then you can subtract it from the pH scale to know the amount of hydrogen ion you have. Now, pH scale, this is a pH scale. I wanted to emphasize the hair. Note, when calculating, we don't calculate the concentration of OH and this when calculating it because they are so small. Because ideally, we should account for the concentration of OH and H hydrogen plus from water, but it's not necessary because they are too small. Now, I want to introduce you to pH. What is pH? pH is the measure of acidity. It's a measure. It's not the actual concentration. It's just the measure. So, for example, if you touch somebody, if you touch the head of a child and the child is sick, you say, ara omo yi gbona. Sorry, I'm speaking vernacular. This child, the body is hot. You just touch the neck, and you say, this body is hot. And you touch if you touch a dead person, this person is cold, though. But you didn't use a thermometer. You just used your hand and you measured it. So pH helps us, just like your hand gives you an idea of how hot or cold the person is. pH helps us to estimate the concentration of hydrogen ion and OH ion. Because if you see those calculations we did, people are disturbing. I'll call it a day. I've done it. I'll call it a day, and then I'll give you what to read, and I'll continue from where we stopped. Please don't disturb my class. I'm begging you, please. Please be honorable people. God bless you. Thank you. So I was saying that pH is a measure of acidity, just like you use your hand to touch a child and say, this child, it must be sick. It's hot. This person must be dead. The body is cold. That is how pH is. pH gives you an estimate of the hydrogen ion or the OH ion. The actual concentration of OH, and that is as seen, is that bracket. We say concentration of hydrogen ion or hydroxide ion is when you put that bracket, open and close, that square bracket. That's what we used to say concentration. But these values are usually very small. See, 1 times 10 in auto-ionization of water, the concentration of hydrogen ion was 1 times 10 raised to power minus 7. If you write it, that means you have 0.000. You can imagine 1, 0, 6 zeros, then you have 1. That value is very small. So pH, this science is called Sorensen in 1909 came up with pH scale. pH will help us measure to estimate this hydrogen ion and hydroxide ion. So it's an estimate, it's a measure of acidity. It's not the actual, it doesn't actually measure the actual quantity of H plus and OH ion. It just helps us estimate how much of them are in solution. And so it told us that pH is equal to minus log H plus. And so it came up with a pH scale that pH scale will only vary from 1 to 14. With this calculation, pH scale will only vary from 1 to 14. So as the value increases, the H plus is decreasing. As the value decreases, the H plus is increasing. And so we have what we call neutral. Neutral substances will have pH around 7. Acidic substances will have pHs below 7, while basic substances will have a pH above 7. Remember I said that as the hydrogen concentration decreases, that for strong acids, the hydrogen concentration increases. For weak acid, the hydrogen concentration decreases. So as the hydrogen concentration is increasing, the pH value is decreasing. As the hydrogen concentration is decreasing, the pH value is increasing. Can you see that? So that's what we're trying to say. So pH is equal to minus log H. We can say this. We can also say pH is equal to minus log K because of this because of this equation. You know, we've established it. So we can equally say pH is equal to minus log K, or pH, or pK is equal to minus log K. They can be used interchangeably. That's why I'm showing you the various versions. pKa is equal to minus log Ka. Remember, because of this equation. So we can use them interchangeably. So don't say, they did not teach me when you see it in exam. You understand the relationship. They are all related. Whether it's hydrogen ion, whether it's Ka, whether it's Kb, whether it's HO minus, you know the relationship. So since this is what's happening, therefore, if you convert it to log, we can say minus log H plus this is equal to minus log this. You see how we arrived at the fact that pH plus POH is equal to 14, which is the basis of this other calculation. You see why we can do this? It's because of this. Should have put that slide before that so that you would have understood better. But it's okay, you've understood now. You get what I mean? So by using the log, yes?
Yes, ma'am.
I told you that in a solution, there's always hydrogen ion and OH minus ion. Together, they give you the pH scale. So if something is more acidic, it means we had more hydrogen ion. It means we had bigger H plus concentration, and it means we have a smaller pH. Yes. So they are all related. That's all I'm trying to explain. And that leads me to the pH scale. So many things in nature fall somewhere. This is just an estimation of the actual OH or hydrogen in it. And the scientist that told us is Soren, a Swedish scientist, was the one who came up with this. So we don't have to deal with two tiny values when doing this kind of situation. And because of this, we're able to come up with pH meters and litmus paper that helps us estimate this very quickly. Now, all these are the fallout of Brønsted-Lowry's concept. I can bring different things up through Brønsted-Lowry's concept. What are the things we get from Brønsted-Lowry's concept? The pH scale could be explained and developed. We got conjugate acids and bases. The concept of conjugate acids and bases from bases and acids was generated. The concept of auto-ionization of water could be explained. Ionization of acids and bases could be explained. Weak acids and weak bases could be explained. Many things could be explained. I've talked about many of them as we were going. So I could bring any of this that the Brønsted-Lowry's concept explains this, except this is OBJ. So you will be able to get that. But the Brønsted-Lowry's concept could not explain reactions occurring in non-protonic solvents. So any solvent that did not have protons, like they did not have H plus, it could not explain how they react as acids or base. It couldn't explain it. It could not explain acidic reactions of oxides and base of it could not explain reactions between acidic oxides and basic oxides because protons are not there. So it could not explain them. It could not explain the why BF3, AlCl3, that is aluminum chloride. He could not explain why they act as acids. He could not explain why they act as acids. He could not explain why they all act as acids. Since they don't donate proton, why are they acting as? No, we have not come to Lewis. No, Lewis concept should not be here. Lewis concept should not be here. Yes, until I've taught Lewis concepts. So if you look at this, can you predict which acid is stronger and which acid is weaker? Looking at their Ka value. You know, Ka value is a measure of the H ion, H plus ion. So the bigger the H plus ion, the more acidic it is. The smaller the H plus ion, the weaker it is. So let's look at this. Which value is the biggest?
HCl.
Why?
That's what
HOCl2.
No, it's HNO2. It's actually HNO2.
HOCl2.
No, HOCl2.
Is HOCl2.
Which acid is the strongest? I said which acid is the strongest?
The second one.
HOCl2.
Acid is the weakest. Acid is the weakest.
HCl.
I can tell you to arrange this in alphabetical. Okay, thank you. I can tell you to arrange this in increasing order in the exam. I can tell you to arrange this acid, giving you some values. Arrange them in increasing order of acidity or in decreasing order of acidity. I can bring for bases. Arrange them in increasing order of basicity or decreasing order of basicity. You can do it with the knowledge you've gained from this lecture, right?
Yes, ma'am.
Yes, ma.
Good.
Yes, ma'am.
Good. You know, I have intelligent students in this class. Want to go to Lewis acid. So I told you that Arrhenius theory of acids and bases had its limitation. Brønsted-Lowry's theory explained many things, but still had his own limitation. So that's why research, there's research. Research is progressive. You do your own, you stop. Somebody will come and take over. Move knowledge forward. So Lewis theory came. He now said, Lewis acids are electron acceptors, and Lewis bases are electron donors. Again, Lewis acids are what? Can people talk to me?
Electron acceptor.
And Lewis bases are
Electron acceptor.
electron donors. So with that, he gave reason. No, Brønsted-Lowry's theory could not explain this BF3. He could not explain how that one is an acid, even though it behaves like an acid. But Lewis acid theory can now explain how this entity, the boron trifluoride, that is BF3, how it is an acid. Because looking at it now, this has 3 valence electrons. And so it involves in covalent bonding. And so it only has 6 electrons in its outermost shell. And you know that to attain the octet state, it needs 2 more electrons. So because it's deficient, any entity that can give it 2 more electrons, it would involve in a dative covalent bond. That way, in doing that, is having that confers on it some acidic property. And so it can attack bases, especially substances that have lone pair of electrons, functioning as an acid. And Lewis bases, like ammonia here, it has a lone pair of electrons. So it functions as a base by donating can react with this BF3. Donating is lone pair to become to act as a base. You can even donate this to a proton. You know, proton has lost all its electrons. So it donates it, and that's how you get ammonium ion. So that way, so Lewis theory is a broader concept. I was able to get this picture, and when I saw this picture, I was so happy with it. I will to explain to you. So the Arrhenius theory, it started the conversation of what is an acid and a base. The Brønsted-Lowry theory expanded it, explained it better. So it accounted for other things that don't produce OH but donate proton and accepts proton. He accounted for it, and so it expanded things we call acids and bases. The Lewis theory even gave us a broader view, it's all encompassing. So inside Lewis theory, you have the Arrhenius theory, you have the Brønsted-Lowry theory. Inside the Brønsted-Lowry theory, you have the Arrhenius theory. Arrhenius theory, it came alone, no? It's on its own, it's just there. So it's like knowledge was expanding. The more you know, the better. So we are knowing more. Maybe it's one of you today, tomorrow will become great scientists that will give us another theory that will encompass all this, because even this Lewis theory we are celebrating, it has limitations. Maybe you are the generation of the future. You are the future researchers. By the time you finish your BSc, you come and do research in chemistry, you might come up with a theory that will overcome the limitation of Lewis theory, because Lewis theory too has some limitations. Let us see some advantages and disadvantages of the Lewis theory. So we are still looking for some scientists that will come and solve the problem. It may be me, or it may be you. What's the advantage of the Lewis theory? It complements the model of oxidation and reduction reaction. So it's now beginning to explain redox reactions to us. It helps us understand redox reaction. Prior to this, we would not have understood redox equation, redox reaction. You know, because it involves redox and oxidation reaction involves the transfer of electrons, not protons. So it suggests that acid reacts with bases when they share a pair of electrons, but there are no changes in oxidation number of any atom. So yes, it look at this aluminium hydroxide reacting with an acid to give us aluminium 3+ and water. In this place, the oxidation state did not change, but yet it acted as a base, even though the oxidation did not change. So it explains this type of reaction where the oxidation number does not change, but you're seeing acidity or something happening. He explains that scenario. And he does so by accepting, he explains it. So he accepts an electron and does that. So it also explains why non-metal oxides such as carbon dioxide dissolves in water to form acids such as carbonic acid. Carbon dioxide would dissolve in water to form that. It does so by donating and accepting. This reaction involves electronic transfer. So he explains this type of reactions to us. So all these kind of things, we didn't understand fully what was happening with other models. But with this model, we now understand what is happening. I will share the recordings of this lecture with you. Okay, I want us to look at this. Which of these acids can act? Which of these is a Lewis acid or Lewis base? Based on the new understanding of acid and bases, you understand. I can even ask you, is this an acid or a base? And why? Well, it's not a theory exam. But which of these is a Lewis acid and which of these is a Lewis base?
NH3 is a Lewis base.
Silver is an acid. Silver ion is an acid.
Because it readily accepts. No, it readily accepts electrons because it doesn't have electrons. It's deficient. That's the word. It's deficient of electrons. Limitation of the Lewis concept of acid and base. He gave generalized idea, including all coordination reactions and compounds. This is not true. He gave generalized idea that every reaction always undergoes electronic transfer. What's happening? Somebody is putting, I don't know, 2 devices are on. The person is interfering, disrupting the quality of our class.
Man, we can't see your screen.
Yes, somebody is causing trouble for you.
Mine is okay now.
Okay. So the limitation is that it gave generalized idea that everything, including all coordination reactions and compounds, that is everything happens strictly by electron transfer. He gave an idea about relative strength of acid and base is not provided, so it does not explain the relative strength of acids and bases. You know, the other one, Brønsted-Lowry's theory did, but this one did not provide, give us idea about relative strengths of acid and base. It's not in line, it does not account for acid-base reaction concept. It does not really account for it. And it has not discussed the behavior of protonic acid like HCl. Does not explain the behavior of protonic acids like HCl. So in life, everything has advantage. The person that is tall is very thin. The person that is fat is very short. You know, the person that is black, maybe he doesn't like his mouth. So there's always in life, there's always a limitation. So even the Lewis acid, we are still finding fault in it. So probably me and you one day will try to fix the faults of it. So these are the limitations of the Lewis acid and base theory. Now, we need to go over to properties of acids and base. You people know this one from your secondary school. So maybe somebody should tell me, what are some properties of acid? I won't sleep there, I'll just run. We know that you know the properties of your acids and base. Acids are usually sour, bases are bitter, bases are slippery or soapy. An acid would change a red litmus paper to blue. Sorry, an acid will change blue litmus paper to red. A base will change red litmus paper to blue. There are many of them are corrosive to touch. What again do you know? You know all the story about how they react with water, how they react with metal. All those scenarios, all those stories, they come under here. So acid and base reaction of acid, physical and chemical properties of acids and base. I can itemize many and then say which of these is not a characteristic of acid, which of these is not a characteristic. I just gave a few. I want you to go and read. Go and get textbooks and read about that because I know you knew many of that before you came into the university. So I didn't dwell on those things. The things I know, you really may not know. They're the things I dwell on. So that is what has happened. So I won't sleep on properties of acid and bases because I know you know it. So, but I'll just run over a few, and I'm giving you assignment. Go and read up on the properties of acids and bases. So acids react with bases to form salt and water. Acids and bases will react with metals, but in different ways. Acid will react with metal to liberate hydrogen. A base, especially alkalis are bases that can dissolve in water. A base reacts with metal to liberate hydrogen and produce a salt too. But the salt is a bit complex, it's not a straightforward salt. It's a complex salt. Just as seen in the equation, metal carbonate will react with HCl to liberate CO2 and form a salt and water. Metal oxides react with acid to liberate hydrogen and form a salt. Non-metal oxide will react with bases. Non-metal oxide will react with bases to form salt and water, such as CO2 will react with the base to form CaO3 and water. Bases and acids will react to form salt and water in a neutralization reaction. So salt can be produced from many of the reactions of acids with base or other substances. And so this leads me on to salt. What are salts? Salts are products of acid and bases, reaction of acid and base in what we call a neutralization reaction. Salt can be formed by a non-metal oxide, acidic non-metal oxide with any metal, with any hydroxide to produce salt and water. Salt can be formed by reaction of oxides with acid, metal oxides with acid. So there are many ways salts can be formed.
Hello?
So these are salts. Salts, you know all the ways salts can be formed. Salts have 2 ions or more, at least 2 ions or more. And salts are usually bulky in nature. Many of them are crystalline, but we have some amorphous salts. Many salts are soluble in water, not all, but many. In molten states, salts generally transmit electricity. There's always electrostatic attraction between the ions that keep them together. Salts are not necessarily always reactions between acid and base, but they are always salts are reactions, are products of reaction between acids and bases, between acid and metal oxides, and maybe between acidic oxides and basic oxides. So salts are products of various reactions. But one thing about salts, we always have anions and cations held together by electrostatic forces that keep them bonded together. Salts, many salts, some salts dissolve in water to give you acidic or basic salt, depending on the type of salt. So if you have a salt produced from a strong acid and a weak base, strong acid and weak base, you have a strong an acidic salt. Strong base and weak acid, you have a basic salt. Weak acid, weak base, you have a neutral salt, but it depends on the concentration of the acid and the base. If the one is more, then it will determine what type of salt is formed. And then all that. So I want you to look at this salt. With this salt here, which salt will be acidic when it dissolves in water? A, B, or C, or D?
C.
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 D.
C.
Which salt will be basic when it dissolves in water? Which salt will be basic when it dissolves in water?
C. Sodium tetrasulfate. D, ma.
Z.
Which salt will be neutral? Is B. B will be neutral when it dissolves in water. Sorry, B will be basic when it dissolves in water. A will be neutral when it dissolves in water. C and D will be
acidic.
D will be acidic when it dissolves in water. D will be acidic in water.
Ma, why?
D
But what
will
about
be
C?
acidic in water. C.
Because ammonia.
In water, we will get a neutral solution. See the answer. Oh, This was I wrote this question wrong. Okay, it's correct now.
Yes. No, my not correct. That one is
There is no
sodium
hydrogen in C.
hydride.
Ma, you wrote NH for Cl10.
Yes, I thought.
If you follow
There's
this
no
anyway,
hydrogen in C.
this
There's no
solution
hydrogen in C.
will be basic. B will be basic. If you follow this question, B will be basic. If you follow this question,
CH5.
D will be acidic. This will be neutral.
2H5.
But this will be neutral too. I wrote a different answer here. But that one too will be neutral because in presence of water, there will be excess water, enough to make this H2SO4. So this is a strong acid, this will be a strong base, so it will be neutral. And then I need to introduce the concept of buffers to you. Buffers, the concept of buffer,
Solution.
one of the fallout of Brønsted-Lowry's theory. A buffer solution are usually combination of weak acid and soluble salt, or a weak base and a soluble salt combination. Buffers are solutions that resist changes in pH when small quantity of an acid or base are added to it. So if you have a buffer solution and you add small quantity of acid, it won't change pH. If you add small quantity of base, it won't change pH. So buffers are needed for certain kind of reactions. So I need you to try out this question. I've given you the answer. Some acid-based questions, because part of the thing I'm supposed to ask you questions, some calculations on acid-based titration, but I don't want to dwell on there because you've done a lot of titration questions before you came to this level. But you've not done a lot of all this kind of pH calculations, and that's why I dwelled there on those calculations. So looking at this, what volume of what volume of 100 molar HCl is needed to neutralize this? So you know that C1V1 is equal to over C2V2 is equal to N1 over N1. That's the equation you use to solve this problem. You write a balanced equation of HCl reacting with NaOH, and then you substitute appropriately. And 10 ml of sulfuric acid from an automobile battery requires 5.0 ml of this molar solution for complete neutralization. What is the molarity of sulfuric acid? C1V1 over C2V2 is equal to N1 over N1. That's how you solve this. So C1 is 10 ml of sulfuric acid. And then the C base is 35. So you put it, so 35 times 2 times 2.1
times 10
divided by
2
10. You are looking for Ca times
C.
You've written your balance equation will be 2:1 or 1:2 based on how you arrange your equation, and you can solve that. So we'll not dwell on the things you know. We'll gloss over the things you know. It's the things you don't know we'll dwell on. That brings me over to oxidation and reduction reactions. We call them redox reaction. We know that, okay, our time is up, so I'll stop. I'll call it a day.
Ma, you can continue, ma.
Who said that? Because I slap your.
We can continue.
Even online,
don't go any class.
Carry on.
Please, I beg.
See, if there's no any class, does not mean that we don't have any other things to do now.
It's okay. All right, okay. We'll continue. We'll fire on next class. Thank you for coming.
Thank you, ma.
I hope you. Somebody had question. What's the question you had? What's the question you had? Somebody had question. What's the question you had? Hello.
Please share the slide.
I'm going to share recordings. I'm not sharing slides. What? Somebody said he had question. What's the question related to what I was teaching?
It's no more yet.
Okay. All right. See you.